In this video, I present the analysis of three-dimensional trusses using the finite element method. I cover an introduction, element equation of space trusses, an example, and finally an exercise for you. By the end of this video, you'll confidently analyze space trusses on your own. The goal here is to derive the element equation for three-dimensional truss systems or space truss used in finite element analysis. To accomplish this, the governing equation for the truss element in one dimension can be used, which is presented in part 2 of Finite Element Method series at Mersat Engineering. Space trusses are efficiently utilized wherever carrying loads in multiple directions is required. Some applications of these lightweight and stiff structures include large span roofs, bridges, towers, mass industrial, and spacecraft structures. Here you can see a transmission tower and a space truss roof. Now I want to derive the element equation for space trusses. For this purpose, we could extend the one-dimensional element equation into three dimensions using the global coordinate system. Here you can see the element in local coordinate system. At each node, we have only one component for force and displacement, u prime 1x and f prime 1x for node 1, and for node 2 we have u prime 2x and f prime 2x. In global coordinate system, at each node we have three components for displacement and forces. For example, at node 1 in global coordinate systems, we have three components of displacement u1x, u1y, u1z. And for forces, we have f1x, f1y, and f1z. Now, the first step to find the element equation of space trusses is that finding the relations between nodal values in local coordinate systems and nodal values in global coordinate systems. For this purpose, first of all, I want to find a transformation of nodal displacement matrix. In fact, I want to derive a relation between displacement components in global coordinate systems and displacement component in local coordinate systems. To find u prime 1x from u1x, u1y, and u1z, we could use the angles between the axis of the element relative to the axis of x, y, and z, and direction cosines of these angles. We could project u1x, u1y, and u1z onto the axis of the element to find u prime 1x. So u prime 1x will be equal to u1x times direction cosine of theta x plus u1y cosine theta y plus u1z cosine theta z. And we could do the same for node 2 and find the relation between u prime to x, the displacement in the local coordinate system for node 2, and displacement components for node 2 in global coordinate system. At the end, we could write these two equations in the matrix format. As you can see here we have the matrix, displacement matrix in local coordinate systems, and on the right side we have displacement metrics in global coordinate system. And what connects these two matrices together is uh, rotation metrics includes direction cosines of theta x, theta y, and theta z. We could do the same for the forces, and at the end we could transform the element equation in local coordinate system to the element equation in global coordinate system. Therefore, we have a relation between displacement metrics in local coordinate system u prime e and displacement metrics in global coordinate system ue. Here re is the rotation matrix, includes cosine of theta x, theta y, theta z, uh, which are the direction cosines. The same relation can be applied to the element nodal force matrices, and we could write f prime e is equal to re f e. Here f prime e is force matrix in local coordinate system, and fe is force matrix in global coordinate system, and re is the same rotation matrix we have found for the displacement. Also, we can write ue is equal to re transpose u prime e, and for forces we could write fe is equal to re transpose f prime e. Now we could apply the same approach we used in driving the element equation for 2D trusses, for 3D element, for 3D truss element, and we could write Fe is equal to Re transpose F prime E at the first step. And instead of f prime e, we could use the element equation in local coordinate system, which is k prime e u prime e. So I rewrite this equation as f is equal to re transpose k prime e u prime e. And here, instead of u prime e, we could write REUE from this equation. So we have FE is equal to RE transpose K prime E REUE. In this equation, on the left side, we have force matrix in global coordinate system. And on the right side, we have displacement matrix in global coordinate system. And what connects these two matrices together is called a stiffness matrix. KE is the stiffness matrix in global coordinate system. So we have the element equation for 3D trusses, which is F is equal to KE UE. So we have found the element equation for 3D trusses, which is F is equal to KE UE. Fe is a force matrix in global coordinate system. Ue is displacement matrix in global coordinate system, and K prime E is a stiffness matrix in local coordinate system based on the uh, axial stiffness of the element. AE is cross-sectional area of the element, EE is the elastic modulus of the element, and LE is the length of the element. Also, we should know that in practice, we use rotation metrics in this format based on the nodal coordinates in the global coordinate system for node 1 and node 2. For example, x21 is x2 minus x1, or z21 is z2 minus z1. Z coordinate of node 2 minus z coordinate of node 1. And we could easily find length of the element based on the x21 u y21 and z21. Now we want to solve an example. We want to determine the nodal displacement for the space truss shown here. All the truss bars have a cross-sectional area of A and an elastic modulus of E. Here you can see 3D view of this space truss. This space truss under the vertical force of P. Also we have side view and top view of this space truss. To solve this problem, we could consider the symmetry of the structure and only half of the truss can be solved. So here we have a 3D view for half of the structure under P divided by 2 force, and we have a side view and top view for this half of the truss. For the solution, the first step is discretizing the structure and numbering the nodes and elements. I consider this element as element number 1, this element as element number 2. I consider this node as a node number 1, this node number 2, and this node number 3. I would like to mention that numbering nodes and element in the global level is completely arbitrary. Also, I determine the nodal coordinates based on the geometry, as you can see here. I have written beside the node numbers for element number 1 and element number 2. Then in the second step, we need to develop uh, the elements equation, or we could determine the elements stiffness matrices in global coordinate system. In global level, the stiffness matrix for the element can be achieved by the multiplication of Re transpose K prime E and Re. K prime E is the stiffness matrix in local coordinate system based on axial stiffness of the element, and Re is a rotation matrix for the element based on nodal coordinates of the element. Now to find the stiffness matrix for element number 1 in global coordinate system, we need to find rotation matrix and stiffness matrix in local coordinate system. Rotation matrix can be achieved based on x21, y21, z21, and length of the element. These parameters can be calculated based on nodal coordinates of the element. To find a stiffness matrix in local coordinate system, we need to find axial stiffness of the element, which is based on cross-sectional area, elastic modulus, and length of the element. For element number 1, cross-sectional area is equal to A, elastic modulus is E, and length of the element is square root of 14 times L. Now we have the stiffness matrix of the element in local coordinate system. Finally, to find a stiffness matrix for element number 1 in global coordinate system, we need to do multiplication of R transpose K prime and R for element number 1. This is the stiffness matrix in global coordinate system for element number 1. Also, I have written on top and beside of this matrix degrees of the freedom based on global node numbers, which help us when we want to assemble a stiffness matrix, matrices of the element to find the stiffness matrix for the structure. Here in this figure, I have written local node number and global node number. At node 1, of element number 1 we have global node number of 1, and at node 2 of element number 1 we have node 3, and that's why I have written these degrees of the freedom on top and beside of this matrix based on uh, global node number 1 and global node number 3. For element number 2 we could do the same, and first of all we need to find rotation matrix based on nodal coordinates of element number 2, and then we need to find a stiffness matrix in local coordinate system, and after that by multiplication of R2 transpose K prime for element number 2 and rotation matrix for element number 2 we could find a stiffness matrix in global coordinate system for element number 2, and I have written on top and beside of this matrix degrees of the freedom based on global node numbers. The next step is assembling the elements stiffness matrices and establishing the global force and displacement matrix to find the governing system of equations for the structure in the form of Ku is equal to F. To find the stiffness matrix for the structure, we know that we have three nodes, and at each node we have 3 degrees of the freedom in x, y, and z direction. So the stiffness matrix of the structure should have 9 rows and 9 columns. We could assign degrees of the freedom based on the global node number on top and beside of the stiffness matrix, and then by referring to the stiffness matrices of the element and finding the corresponding entries, we could fill out the stiffness matrix and find the stiffness matrix for the structure. To find displacement matrix, we know that at node 1 and node 2, all the degrees of the freedom are closed. So we have zeros on these rows for displacement matrix. Also at node 3 in x direction, displacement is closed. The movement uh, is fixed, so u3x is equal to 0 as well. But in y direction and z direction at node 3 displacement are unknown, and we need to find u3y and u3z. To find external force matrix, we know that at node 1 and 2 all the uh, movement are closed, so we have unknown reactions at node number 1 and node number 2 in all direction. At node number 3 reaction uh, in x direction is unknown, r3x, but external force in y direction is known, is equal to 0. We don't have any applied external force in external forces in y direction, but in z direction external force is equal to minus p divided by 2. Finally, by solving the global system of equations, we could find the unknown displacement for the structure. This is the system of equations for the structure. This is a stiffness matrix, this is displacement matrix, and this is force matrix for the structure. Because the displacement in all direction for node 1 and 2 are closed, also the displacement in x direction for node 3 is closed. we could only consider this part of the system of equation, which is a system of equations with two unknowns, u3y and u3z. By solving this system of equation, we could find unknown displacement in y and z direction at node 3, and because of the symmetry in x direction, the displacement is equal to 0 for node 3. So back into the structure, we have solved this space truss under the vertical force of P, and because of the symmetry, as I mentioned, in x direction, the displacement at this node is equal to 0, and in y direction and z direction, we have found the displacement which are in the opposite direction of the axis y and z. At the end, we have an exercise for you. Determine the displacements of the space truss shown below. All members have the same cross-sectional area. A is equal to 500 square millimeters, and elastic modulus E is equal to 2 times 10 to the power of 5 megapascal. The parameter L is 200 millimeters, and the applied force P is 5 kilonewton. Also, I would like to mention that the follow-up videos on the finite element method will be posted. Thank you.